Hi there, this is Patrick Degenar, your course lecturer on the bioelectronics course. So in this particular session, we're going to cover the SPICE tool and just basically get you up and running and get you started so that you can do the virtual labs. SPICE is a method for simulating circuits. It dates back quite a few decades now, but the specific SPICE tool we're going to use is something called LTSpice from Analog Circuits, and the link should be in the notes that I provided you. But you can download it from here if you can see it from here. Otherwise, use the link I've sent, and you can download it for either Windows or Mac. It's free. Click on one of these. You get your little download thing and then install it. It should only be about 100 megabytes on your computer, so it shouldn't overload your laptop or whatever other utility you're using. So once you've installed it, it'll look like this. I'm just going to overlay my screen, so I've got a little bit of a writing tool for writing for you guys. But once you've got this specific screen, you can create new schematics at will. And if we look around the top, okay, you've got your standard save. This run command is for running your simulations. I'll describe that in a bit. You can set your windows. For example, this is a previous circuit I was going to demo for you, but we're going to do things from scratch. And there's your background. And then, of course, you've got cut, you've got copy for particular circuit components, obviously print commands, and then you've got the components themselves. So let's run through this. The first thing we're going to do, we're going to create a very, very simple potential divider circuit just to get you started and understand the simulation methods. So first of all, we're going to put down two resistors. And if you roll the wheel, you can zoom out. If you, depending which way, you can zoom in and out if you like. And you notice I've still got a resistor there. Press escape to get rid of that particular mode of operation. The next thing we want to do is to insert a voltage source. Now there's no voltage sources up here, so if there's something that is not here, you click on components, and then we can type in voltage for voltage source. It's already in there. Click OK and click, and then of course to get rid of this thing you press the escape button. The next thing we're going to do is to draw a wire, because you obviously need to connect up your circuit. So click, 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 and then click. Oops. Right, try it again. And click from there to there, and from there to here, and in you go. And escape to finish. Okay, so now we've got these, now we've got a basic circuit. This is called a potential divider circuit. And, in this particular circuit, no, I'm trying to get this pen. Yeah, so in this particular circuit, the equation is, V is equal to R2, if this is your V out, is equal to R2 over R1 plus R2. And you'll notice here that the R1 and the R2 are the names of the components, and these values, in this particular case we've got R as a value, these define the actual values. Now if you leave it as a variable R, it's something you can change in the simulations, but for convenience we are going to change this value to a set value. So let's click on this and let's set it to 10 kilo ohms. So you right click on the device and then you type in the value. We're not bothering with tolerance or power ratings. They're for more advanced simulations. And then for the click OK, and then for the R2 we're also going to give it a value, and we're going to give it the same value of 10 kilo ohms. Now if you remember before, that we said that the V out, this point here, V out is equal to R2 over R1 plus R2. Well, this is going to be 10k over 10 plus 10k, or 10k plus 10k, which is equal to 1 over 2 of your V in, yeah, or your V1. So this is basically going to be your half V1. So we're keeping things very, very simple for the purposes of just understanding how this tool works. So press escape from my demonstrator tool. Now, before we start a simulation, we should click on this voltage source, and we've got two choices. The first choice is to simply give it a value. Let's start with a flat value, DC value of 1 volt. Now, there are a couple of types of simulations that we can run. So let's look at the simulation tool, and we're going to click on Edit Simulation command. So this is where we can edit our simulations, and we've got a few choices. We've got transient, so just look at what's happening to the circuit passively in time. We've got AC analysis. Look, if this is a frequency source, what happens to a particular value as the frequency increases. And then the other one is a DC sweep. What happens to an output voltage as you sweep an input voltage? So let's start off with the transient, because that's the easiest. And remember, we've got just a fixed voltage, so nothing should change in time. And I'm going to simulate for 10 milliseconds. So I'll just do the stop time as 10 milliseconds. Okay? And you get this little bar, and you can just define that simulation somewhere in the middle of the circuit. Okay, so everything's set to go. And we can click on this run command, the little guy fast moving, or else you go to simulation and the run is in there. And this circuit does not have a ground point. Now, this is a very important aspect to Spice. If you look at this simulation tool, this voltage has a positive and a negative, and a line is going through these resistors and down and back up again. So actually the circuit is complete. However, in the Spice tool, you always have to define a ground point. So let's put that in. So this is a ground, and we're going to connect it to the bottom, connect it in effect to that minus. So if you see that error, it's simply because you haven't put your ground in. So now we're going to run it, and we get this black screen and nothing. And the reason for that, we've defined our simulation to be a transient simulation. So if you look at the x-axis, it's 0 to 10 milliseconds, everything is there. The problem is we haven't defined our outputs. So let's define two outputs. First of all, let's define this line here. So if you click on a line, you will get a voltage. And in this particular case, well, this is a fixed DC voltage, and over that entire time, we have got 1 volt, which is what you would expect. If you click on the in-between of these two, and if you remember our calculation, it should be half of that value. And yes, lo and behold, we get half a volt in between the two. Now, this isn't, a very convenient way of simulating things. So let's do something, it's all DC, it's not changing in time. So let's look at something that's actually changing in time. So first of all, let's get rid of this. Let's go back to our simulation. Right click on our voltage source, and this time we're going to click on advanced, and we can choose different types of voltage sources. Now we're going to choose a sine wave voltage source, and we can do offset. Let's have a 0 offset. Let's have an amplitude of 1 volt. So this will go between plus minus 1, or it'll go between plus half, minus half, and we'll set a frequency of 1 kilohertz. And if you remember, we simulated for 10 milliseconds, so that should give us about 10 waves. Okay, so there's our voltage all set up. Let's run our simulation again. And this time, let's look at the top and let's see what's happened. So we're going from 0 to 1 to -1. Okay, when it says amplitude, it means plus or minus 1 rather than 1 necessarily. These different simulators have different definitions of amplitude. And if we click in the in-between part, you'll see this is probably a little bit difficult depending on your YouTube, but there's a blue, quite faint, but there's a blue oscillation here, which is basically at half the amplitude. So whereas the voltage source gives plus or minus 1 volt, we now have plus or minus half a volt. So that's your basic transient analysis. What is happening in time? Now, there isn't just transient analyses that we want to do. Another type of simulation is to say, well, okay, what happens if I change the voltage? Now, I've already set this thing to be a sine wave, but it doesn't really matter. What we're going to do is we're going to name the source of the first. We're going to do a sweep. We're going to do V1. So we're going to sweep the value of V1, and then we're going to start a value of 0, and we're going to go up to say 10 volts. And we're going to do these in increments of, let's say, 1 volt. So we can click OK. Here's our DC sweep. Now, you may have noticed we've got a transient analysis and we've got a DC analysis. And, oh, sorry. And if we click now and run, oh, yes, of course, we have to see what's happening here. Now, for the DC analysis, you'll see as the sweep goes from 0 to 10 volts, we go from 0 to 5 volts because we're halfway in between those two resistors. So again, that's what's called a DC sweep. Now, a little bit later on, we will be using AC sweeps. And the easiest way to see an AC sweep is to use perhaps a capacitive filter in there. And let's click this on a line. Whoops, there and there. Okay, so now that we've set this up, the first thing we need to do is to give our capacitance a value. So let's give this let's give this capacitance a value of, let's say, 1 picofarad. And then in order to illustrate what we're going to do, let's do a transient simulation once more. So let's go to transient simulation, and we'll do a 10 milliseconds stop time, and then we can simulate. And again, as before, we need to click on a value, and at that 10 picoseconds, it's going up and down. It's supposed to be one volt, but we only get half of that because it's 10k and 10k, and it's a potential divider with half the value coming out. So everything is as before. That capacitance isn't doing anything. So let's try this again. Except this time we're going to give a value of 1 nanofarad. And let's see what happens. Let's simulate again, and exactly the same again. Okay, nothing happened. Now, let's give a value of 1 microfarad. And now let's simulate, and click on this line just above, and look, we're now at 28 millivolts. So we aren't half a volt anymore. We're down to millivolts. So clearly, the current is now bypassing this R2 and starting to go through C1. But if we want to know, well, at what frequency does it start to bypass, or capacitance it starts to bypass it at 1 kilohertz. This starts to become a little bit problematic because I mean, we can calculate it, but in terms of simulations, you know, this becomes trial and error, which is not an ideally efficient way of doing things. So what we really want to do is create what's called a Bode plot, and that can be achieved by running a AC analysis. So if we go back to our simulation tool again, now we can go to our AC analysis, and we're going to do a let's do a decade sweep. The number of points per decade, we're going to do 10, and we'll do a frequency between 1 and 1e to the 6. So for this 1 microfarad capacitor, we're going to find out where it's all going to cut off. And now we've set up the simulation, we can run our simulation. We're going to click just above the capacitor, and we get what's called a Bode plot. So this is an AC simulation, and what you see in the x-axis is frequency, and what you see in the first y-axis, this is in dBs. So let's get our pen into action here. So a dB, just in case you don't know, a dB is minus 20 log of I1 over I2. So, you know, so your new frequency compared to your original. And we use dBs for gain because gain tends to be a logarithmic process. And we normally say that the cutoff is at minus 3 dB. And if you calculate back, that's equal to basically half your original signal. So, whoops, sorry for that little red thing there. So if we start off here, roughly speaking, our 3 dB point, we can start to zoom in, but I won't bother for the sake of time, for the sake of brevity. So our 3 dB point, our 3 dB cutoff will be somewhere around here. Now you also notice this other axis which has got degrees. So this axis is in dBs. This is effectively a logarithmic form of amplitude, and the degrees refer to phase, and this becomes important in feedback, but I won't cover that. I won't cover that in this particular lecture. So I've now finished for this particular demonstration. The key objective here is to get you started. Please try to do this series of simulations yourself. The key objective is so that you understand how to put in simple components like resistors, voltage sources, how to simulate a transient analysis, how to simulate a DC analysis, and how to simulate an AC analysis. And you will get 3 particular virtual labs, and I will give you a brief introduction to each with its own separate video. Thank you very much, and see you soon.